Next topic is defects in solids. Here the defects in solids arises due to missing of ions or dislocation of ions. That means if ions are missing from the crystal, or if ions are not present in their portions, if they occupy in another portion of crystal, then defects arises. Here there are two defects, one is line defects, one more is point defects. No need to discuss about this one, point defects. So here also same definition as in defects in solids, that is the defects arises due to missing of ions from the crystal or dislocation of ions. Here these point defects are classified into three types. They are trichometric defects, impurity defects, non-stoichiometric defects. These are important. Now we are going to discuss about these three. First defect is trichometric defect. The defects in which without change in chemical composition are called stoichiometric defects. The defects in which without changing in chemical composition is called stoichiometric defects. Again, these are classified into two types. They are Schottky defect and Frenkel defect. Schottky and Frenkel defect. What is the definition of Schottky defect? This defect arises due to missing of equal number of cations and anions. This defect arises due to missing of equal number of cations and anions is called Schottky defect. For example, I take one crystal A plus B minus A plus B minus. In this crystal, see here two vacancies are there. Here B minus escaped, here A plus escaped. That means one cation, one anion and one cation are missed, or two cations and two anions should be missed. Then such a defect is called Schottky defect. That is the meaning of definition, that this defect arises due to missing of equal number of cations and anions. Frenkel defect means this defect arises due to dislocation of cation or anion. Dislocation. That means, I told you already, dislocation means if that ion is not present in their portion, if it occupies another portion, that is called dislocation. See, if you see the example, then you get idea. Here A plus is present between these four ions. Actually, it should be presented at here only, but it occupies here. That is dislocation. That defect here, not missing of ion from the crystal. Here cation or anion occupy another portion, not their portion. That defect is called Frenkel defect. This defect arises due to dislocation of cation or anion. Next, if ions are missing from the crystal, automatically density decreases. Here ions are not missing from the crystal, so the density remains constant. In this defect, coordination number is low. If ions are missing, automatically coordination number is low. Here ions are not missing, so that coordination number is more. In this defect, the difference in the size of cation and anion are very less. That means both cation and anion are in equal size, both are having almost same size. In this case, in this defect, the difference in the size of the cation and anion is more. Here both are having same size, here both are not having same size. That's all. Here the example for this defect is NaCl, KCl, AgBr. Here the example for this defect is AgCl, AgBr, Ag. Here one important point is that is AgBr. AgBr comes under both defects. That means it shows both Schottky and Frenkel defects. This is very important bit. Which crystal shows both Schottky and Frenkel defects? The answer is AgBr. So this is about stoichiometric defects. Next, impurity defects. This is very important for competitive level. So here the definition is this defect arises due to addition of external substance or impurity to given crystal. This defect arises due to addition of external substance or impurity to given crystal, then this defect will arise. Suppose this is NaCl crystal, Na plus Cl minus, Na plus Cl minus, this is NaCl minus. So yeah, positive ions and negative ions are present in alternative position. This is very important point. Suppose if you add this external substance, that is what, MgCl2 to this crystal. If you add this MgCl2 to this crystal, then what happen? This Mg, here Mg contains plus 2 charge. We know that Mg plus 2 cation replaces 2 cations. Why 1 Mg plus 2 replaces 2 sodium plus ions? Because here 2 sodium plus ions having plus 1, but 1 Mg having plus 2. So that this 1 Mg plus 2 can replace 2 sodium ions from this crystal, and finally it becomes like this. What happened here? 1 Mg plus 2 replaces 2 Na plus ions, and among 1 Na plus and 1 Na plus ion place occupied by Mg plus 2. Finally, one vacancy will be formed. If you add 1 MgCl2 to NaCl crystal, one vacancy will be formed, and 1 Mg plus 2 ion is present in that crystal. But finally, stability takes place. How can we say that stability? Stability means number of positive charges equal to number of negative charges is there in a crystal, that is stability. Here, even though one vacancy is formed, but here stability is same, because see, charges, positive charges how many? Plus 2, plus 1, plus 1, total 4. Negative charges minus 1, minus 1, minus 1, minus 1. So number of positive charges is equal to number of negative charges. Automatically this gets more stable. But the point is what? If MgCl2 is added to NaCl, 1 Mg plus 2 replaces 2 Na plus ions, and 1 vacancy is formed, that is what? Cation vacancy. If suppose if AlCl3 is added to NaCl, suppose AlCl3 instead of MgCl2, we know that Al having plus 3, then 3 Na plus ions missing, but 2 cation vacancies are formed. Why? Because out of 3 Na plus ions, 1 vacancy occupied by Al plus 3. Then remaining 2 portions are vacant. That is why 2 cation vacancies are formed. So this is about impurity defect. Next one is non-stoichiometric defect. Non-stoichiometric defect means without changing in chemical formula. But here, if chemical formula is changed, that is called non-stoichiometric defect. So the definition here is the defects in which with change in chemical composition are called non-stoichiometric defects. Here these are again classified into 2 types. They are metal excess defects and metal deficiency defects. Metal excess and metal deficiency defects. Metal excess defects means if a given crystal is heated, in the presence of metal atom, then anions comes out from the crystal leaving behind electrons. That means when the anion comes by leaving electron from the crystal, these electrons are called F centers. That means those leaving electrons are called F centers. Due to these electrons, the crystal exhibits color, magnetic property and conductivity. Those electrons are called, this is important point, those electrons are called F centers. Due to the presence of those electrons, crystal exhibits color, magnetic property and conductivity. Suppose for example, I take again NaCl crystal. We know that in NaCl crystal, positive ions and negative ions are present in alternative positions. Suppose if that crystal is heated in the presence of sodium atom or without sodium atom, then what happens? that anion comes out from the crystal by leaving electron. See, one Cl minus comes from this position, or we can write here also electron by leaving electron. Then finally what happens? Crystal becomes stable. How can we say that number of positive charges is equal to number of negative charges? That is stable. Then how can we say that here chemical composition changes? Here Cl minus left from this crystal. That means one Cl minus left. Then automatically there is a change in composition. That means there is change in formula. That is why this is called non-stoichiometric defect. Then one point is there here. Why it is called metal excess defect? Here Na is the metal, Cl is the non-metal. We know that already. In this crystal, metals are more compared to non-metal. That is why it is called metal excess defect. Next, this defect is also arised by heating the crystal without metals. Next one, metal deficiency defect. This defect arises due to crystal having different oxidation states of the metal. That means when crystal having two different metals means metals having different oxidation states, then this defect will arise. Suppose I take FeO crystal. In FeO crystal, Fe plus 2, O minus 2 are cations and anions. When those are present in different, when those are present in alternative position, then crystal will be formed. That is the FeO crystal. Suppose one Fe plus 2 is occupied by Fe plus 3, automatically one cation vacancy will form. One cation vacancy. If cation vacancy will form, then that means what? Cations are less compared to anions. That means metal ions are less compared to non-metals. That is why it is called metal deficiency defect. Next, here one problem is given regarding this one. Calculate the number of Fe plus 2 and Fe plus 3 ions in Fe 0.95 oxygen 1.00. This problem comes under metal deficiency defect. In that question, Fe 0.95, O oxygen 1.0. That means 0.95 iron atoms are present, 1.00 oxygen atoms are present. What we have to find? We have to find number of Fe plus 2 and Fe plus 3. That is the meaning of the question. First write the formula. Fe 0. Remove decimal points. Then it becomes like this. Fe 95 O oxygen 100. So what is the question? We have to find Fe plus 2 and Fe plus 3. That means this iron contains two charges, plus 2 and plus 3. That is the meaning. So we are assuming that let Fe plus 2, let Fe plus 2 equal to x, then automatically Fe plus 3 equal to how much? 95 minus x. Or you can assume Fe plus 3 equal to x, then automatically Fe plus 2 equal to 95 minus x. You can assume either of that one. Here the fundamental basic point is, this is the important point. The fundamental basic point here is the total charge of cation is equal to total charge of anion in any crystal. The total charge of cation is equal to total charge of anion in any crystal. So that 2x plus 3 into 95 minus x, 2x plus 3 into 95 minus x is equal to 100 into 2. What is the 2? Oxygen instead of oxygen. Actually minus 2, we should not mention negative signs here. 100 into 2. What I told you, total charge of cations regarding the atoms is equal to total charge of anions regarding the atoms. So finally we get x value. From that we can get Fe plus 2 and Fe plus 3. Again we have to mention the answer in decimal points. We got 85. That means in decimal 0.85. In this case we have got 10. That means in decimal point 0.1. So this is the way to calculate this type of model. So this is all about solid state. Thank you.